Good evening in Japan. Japanese time is around 1 a.m. 1 o'clock. I just couldn't fall into the good sleep, and so I try to read the next theme of CS common source amp and source follower, and their input refers thermal noise. Before diving into delivering the thermal noise expression, we need what's the topology, what the topologies of these amplifiers, and what is the gain, and what is output resistance, and what is how to calculate easily using Thevenin or Norton equivalence. But fortunately, we have good textbook of design of analog CMOS integral circuit written by Zavi, second edition. We better accompany this book, and followed by this textbook, we can proceed and enhance our understanding of these themes. First, on page single stage amplifier, on page, let me see, cascode stage, before cascode stage, on page 70 something, 70, oh yeah, there's a source for on 71 and 72, very important approach, simple approach to gain insight or derivation of voltage gain. And on page 60, or 58, around these pages we can get some useful derivation of CS stage with current source load. And simply saying, we know, or some rules of thumb says amplifiers like single stage, like C common source amplifier, this is current load, and this is NMOS input being there, and this is output. Usually Uh, the simplified approach to get voltage gain is well known as AV equals resistance or impedance looking into the drain divided by resistance or looking into the source. In this case, there's no degeneration resistance, just this is if moving some voltages with modern ideal driving source voltage or this source node, and they find how much impedance, how much resistance are there looking into the source. Input is shorted, so this gate source voltage is oscillating, modulating gate source VGS means there's 1 over GM of resistance looking into the source. And looking into the drain, there's RO1 and RO2 in parallel, because this is small signal equivalence. The VDD and ground both are AC grounded. So GDS, say RO or P channel and N channel is parallel resistance looking into the drain, and looking to the drain is RO P in or 1 or 2 and RO N in parallel, or so parallel combination of this. So simply GM RO load RO input in parallel. If this is some load resistance, passive resistance RL much smaller than RON, so in parallel this is approximated by RL. GMRL, this is R out, and this is transconductance of input animals. Resistance looking to the drain divided by looking to the source. But that is looking at the source. But things are not so easy. Things going not like that every time. This is input for SF, and this is some bias VB, and this is source of input animals, and this is V out, VDD, and ground. The source is following input voltage, just about around VTH. Threshold voltage of N channel is nearly fixed, and this V out is following VS. V out is source of input animals. So this amp is called source followers. These are source followers like this. But resistance looking at the source is this, and resistance looking into the output drain is this or this. Usually, this is not. This is BDD and connect AC ground, and we can't move this around. We just something we can get just from here V out some signals amplified. But every nearly equal 1 or less usually, but this is a buffer amp usually used for buffer amp, and although this gain is not much, there's gain, and this is no gain, fixed voltage, and so we relevant node is V out, not VDD. Looking into the V out, resistance looking at the V out divided by something, this doesn't fall in this case. Simply, what is drain, what is the source? Sometimes this is useful, but in this case, we have another method to get a V, like this textbook, so page 712 of second edition. Let's please take a look at these pages of this textbook and remember yourself again of this derivation for source followers. 71 and 2. Page 71, figure 339, calculation of the output impedance of a source follower. For source follower, output impedance is this book. We use small signal equivalent circuit for this. This is GM M1 M2 1 R01 in parallel 2, and for this R out, to get R out for small signal, this is GM M1 and M2, and this current is GM plus minus V1, source and drain voltage V1, and current is from AC ground, and in parallel with that, because the source voltage of this M1 is one step higher, or one step higher voltage, and the VS source voltage and base voltage, this base voltage VB doesn't is not zero like this case, so there's a back bias gate, back gate effect. Back gate means N plus, for N channel, N plus P substrate or P where, and this node is usually grounded, but this N1 source node is B out, the floating, and not VSS, and V drain is VDD. This and this is gate oxide, and this is gate, and VG, and this is this is Vs, but usually V out is not connected to floating P where. This is usually in many cases P substrate, which is not which couldn't be floated. Most least the least smallest most small least small least voltage. So this is the Vs. V out is Vs, but P substrate is back gate. This means this P sub. This is front gate. In a sense, this is back gate. P sub is grounded. 0 volt. AC 0 or DC 0. So Vs floating P out output versus VB, which is 0, has some amount of voltage in this case. So because this is non-linear bias saturating area, working saturating area, producing some bias current for this end, source floors. So this is not this couldn't be 0. Like gate is constant, like for M2, V out versus IB like this, and this couldn't be going to 0, even if L is large. This couldn't be 0 for constant bias IB. Some smallest limits is around there. So Vs is positive something and P sub equals 0. Back bias get base to source to base voltage exists, and this is GM V1 and this is GMB VBS. Okay, VBS, if back gate is higher than source, the threshold is down, decrease, and the current is going through added. So this direction, current is added, so this is right. If this is VSB, vice versa, and this is in parallel, this is this is minus node of V1, and current, we are applying voltage source, but voltage Vx plus minus here to find R out, because this is constant current and AC is for small signal equivalence. This is just opened. Constant voltage is shorted to ground. Constant current opened for small equivalent circuit. So this is opened and applied some voltage to find R out, looking into this output, and this is the equivalent circuit, and this is IX, and R out equals, of course, Vx over Ix. In here, R out equals 1 over GM plus GMB. Finally. two admittance added and transversed to get R out, or GM1 1 over GM1 resistance in parallel with 1 over GMB equals this. Okay, so there's a parallel resistance 1 over GM and 1 over GMB, getting 1 over GM plus GMB. This is R out for SF. Now R out times GM, R out times GM equals nearly AV, or is it right? Or we are going to check that. Driving source follower including body effects, equivalent circuit. So looking at figure 340 on page 71, bottom of the 7, on bottom of the page 71. Sorry to erase that. This is the same, and looking at excluding GMB1 and V1 and looking at these area section, Vx applied and 1 over GM resistance here to ground. So this is equivalent to this, just from Ohm's law. 1 over GMB is one of the nodes is grounded and the another node is applied Vx, and here there's controlled voltage, controls current source GMB1 from ground, AC ground, and here from here to here there V1 VGS of M1. First step, we can look this area like this equivalent circuit. And next step, how to get AV voltage gain of this source follower. Page 72, figure 341, representation of intrinsic source follower by Thevenin equivalent. Thevenin equivalent of source follower is written from this by this. Input is referenced by ground here. So we are looking for voltage gain, voltage V applied here, reference to ground, and plus this is V1, and this is current controlled voltage controlled current, and this is ground, AC equivalence. This is output, V out, and this is first step equivalence of 1 over GMB. And we know from this looking into the source, the same as this. Looking at source of M1, 1 over Gm is the resistance looking at the source. So, looking at this equivalent circuit, and make this more simple using Thevenin equivalent. How can we do to simplify this circuit? Not using this current source, just passive GM referenced resistance. And the second schematic, right one, represents the equivalence. Do you know why this equivalent circuit is relevant for this or equivalent? Why this is equivalent? How come we get this equivalent circuit? So these are the point for source follower to get voltage gain in easy way using Thevenin equivalent, but not tough, but you need some insights or trained minds to get these expression. But it's very simple. Simple Ohm's law. From Ohm's law, this is ground, but this is not ground. This is plus minus V1. V1 times Gm1 is this current. And V in R out. This equivalent is like this. Well, this current, if this is IRO equals V in, where R0. So R0 equals V in over I. This is Norton equivalence of this Thevenin equivalence. Vice versa, if V in equal I times RO, we can write equivalent circuit like this. V in series with output resistance. So we need this expression for this. This is ground, and upward to I of GMV1. Okay, and V1 and V in how V1 and Vwin is related. Looking at this, V1 Vn equals not V1. This is V out. V out plus V1. Here's V out, V out, and plus V1 going to V in. So but the resistance looking into the V out 2 looking into source is 1 over Gm. Looking from here 1 over Gm when V in equals shorted. When V in equals shorted, when V in equals shorted, that's 1 over Gm from here. This means when V in shorted to ground, just arrow, and just arrow is 1 over Gm. So this is simple. From simple insight, we write these parts like this, like the right side of the picture, but just insight, logically saying this I equal GMV1 and this Vin equal what Vin? This Vin is not Vin, just Vin, not just Vin. This Vin is driving output resistance with output resistance this RO, and this Vin is here. Resistance looking at source. Finding resistance looking at source, V equals 0. So V1 minus V1 minus V1 G minus G I from J. This is I GMV1, and this means V in here is V1, this voltage. Because V1 is V1 one. This current is this current GMV1. Okay, and this is V in from ground to this gate node. And if this is V1, RO equals GM, and GMV1 in parallel with 1 over GM, and multiplying this GM 1 over GM times GMV1 equals V1. Multiply this V1, we get V1. This, we get this V1 and RO of 1 over GM equivalent. V1 is applied and RO exists, or GM V1 in parallel RO 1 over GM exists. So here we must not be complicated. In here, this is the cause, but the actual voltage to need to get equivalence is applied voltage of source to gate to source voltage of V1. And this is cause, but we don't need this value. We need representation of V1 and this GMV1. Looking into the output resistance is for M1 equal 1 over GM, but the cause is V1, this V1, and this V1 gets leads to GMV1, and so Thevenin equivalent is changing this node using this V1 to 1 over GM, but this is a problem. This is not V in. We need V in to get AV equals V out over V in. We need V out over V in, not V1. So again, I'm very complicated. I was very complicated, and also again I'm now being complicated. V in plus minus V1, and there's current GM V1, and equivalently to in parallel GMB 1 over GMB. Here this is V out. So, and we need V out over V in, and use Thevenin equivalent changing to like this. But R out from here, R out V, not V1, we need V in, and equivalent R out. So, V in, ground to V1 GM, ground to V1 GM. this can be. Do you know why this can be V in? V1. From this we just simply AV equal voltage divider of 1 over Gm plus 1 over GMB 1 over Gm over this. This is GM this plus this plus GMB 1 over Gm plus 1 over GMB 1 over GMB divided by this is resistance, and this is going to be simplified what GM GMB Gm plus GMB GMB cancelled, and as expected we get Gm 1 over Gm in parallel 1 over GMB times R out times Gm Gm or Gm divided by Gm plus, easy to remember, or Gm times 1 over Gm in parallel 1 over GMB. Base resistance is conductors base voltage base current effect body effect conduct resistance body effect resistance in parallel with source resistance is this output resistance times transconductance Gm is the gain of source flow, but we need to find this equivalence from there for this, but this is need to be V in, not V1. Do you have any idea from here to there? If we can get this and Gm R out, R1 in parallel R2, we easily derive the thermal noise of these input reflected noise of these CS and CF. But I had been in a trouble to find out how to change from here to this, and one day I realized that the textbook is right, and we need to go from here to there to get V out over V in. And again tonight I found myself very complicated in finding out how to go from there to here, because this seems to be V1 but this is V out. This is V out. This is V out. V out. V. This is why this looking at the drain there. Mama GM. Looking to output to open output. Input shorting. No, we need just overthrow to get Thevenin Norton equivalence, but for AV we need V out and V in, not V1, gate source voltage, gate to ground voltage. Well, it's not so difficult. Please, we must say again what's V in and V1. V1 is gate to V out source voltage, and V in equals gate to ground voltage, and this is small signal equivalent. V in difference is appeared almost equally V in to V out. Really? So V in AC meaning equals V1. As far as if V out doesn't move, but V out is V in AV. V in move, V out move, with the ratio of AV. So V1 not equals V in a small signal sense. In a small signal sense, V in not equals V1. Okay. Just a confirmation. V1 not equals V in also in a small signal sense, because V out moves. V1 move, V in move, V out move. But V1, if V1 doesn't move, GM V1 equals 0. But in small signal sense, GM V1 equals 0 if V1 equals 0, which means V in and V out not approximately, exactly follow the V out exactly follow V in. Delta V in and is the final delta V in, but no delta V1, and this is 0. So we got no voltage gain. Oh, V1 must be moved. V1 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 gate to source voltage. Yeah, of course. V1 GMV1 or GMV BBS, and the V1 is applied from V in. V move So I was and I am complicated. Why finite GMV1 exists? Because V1 varying, but V out varying also, and V in cause V1 V out varying. No, V in cause V1 variation cause the current variation, and GM times 1 over GMV get the V out variation. So equivalently, it's some kind of weird trouble in V1. V1 ground to V1 GMV V1 V if V out is shorty, V in equal V1. V out shorty. This I'm looking to the main one of GM1 what the kind of this? Just ground here. Ground to 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 here. This is ground to be out. This in parallel with some R is Norton equivalence attached here equivalently, but we need to know R. But this is transverse to this is way out. And this is R1, this is this. V equals R GMV1. This open voltage equals V equals what voltage rejecting this one, looking into from the V out equal RO, and looking to rejecting this resistance, looking to the source V out equal 1 over GM. But we just write V in to change. This is V1. About V in change, V1 change approximately equal for this is small signal. This is just maybe approximation, but approximated good approach. Equivalent. V1. So GMB minus V out flowing through 1 over GMB makes the out. Simply this, we can get this equation and change this 1 GMB times GMB out equals GMB in. So B out over V in equals GM over GMB plus GM, which is GM times 1 over GM in parallel 1 over GMB as expected. And this is the same. Actually, this is the same of this V in 1 over GM 1 over GMB, and this is V out. Interestingly, this and this is the same. Erasing V1 using this equation and just Ohm's law we can get this. So just Ohm's law we can get this equivalent from for Thevenin equivalent. why V1 equals V? If V1 equals V in, we get, no. If V1 equals V in, we get, it doesn't, couldn't get this. Just like change this V in. We don't get there. This get this and this, and this gets this and this is right. This approach is right, this approach is right, but exchange V1 to V in doesn't read this expression. GM V in divided by GMB equals V out. So V out over V in equals GMB over V, GMB. So there's no GM. But so this is V1, and this is V1, and this is V in, and this is V in, and 1 over GM, and V out. Okay, I see. But if you know before that, at this time, I understand, and I remember I understood last time. Why my understanding complicating? From this, exactly V1 equals V minus V out. So we need what? GMV1. GMV in. This is GMV in minus V out. Ground and R, and then the bean and 1 over GM. And this is V out, just V out. So this current I out equals V in minus V out, or V out divided by 1 over GM RO. So just this. This is 1 over GM, resistor leaking source. This time this going to be minus V out, which is V minus V out. And this current is this current. So this is right. Correctly 1 over GM and 1 over GMB in series, and this is V out. This I equals this I. GM V out minus V in, or V minus V out. GM V minus V out. This current is GM V minus V out. This current is this current. V1 equals V in minus V out. So GM V in minus V out. GM V minus V out is this, and in parallel looking into the GM, 1 over GM. So actually this is equivalent. These two are equivalent, and this is equivalent. We don't need this equivalent. From just using this equation, we can get the same result for AV, V out over V in. Okay, but good insight like Lazabi sensei reduces this just a little bit complicated active current source and resistance combination to more simple resistance, just resistance schema, Thevenin equivalent, and from side, just one side we got V out over V in as a voltage divider. But from this, just a little we need to write equation, not to get it wrong. But if from this and to if you can rewrite from this to this, you simply get AV. This is not a voltage gain AV. So source follower. Okay. V1 equals V in minus V out. So this is GM V1 V in minus V out. And resistance looking into the source equal 1 over GM in parallel this, and this time this is this current. This voltage, not this voltage. This voltage.